Remember that a buffer solution consists of a weak acid and a salt of its conjugate base, or a weak base and a salt of its conjugate acid. Buffers react with strong acids and strong bases and resist changes in pH. However, we do have a buffer capacity. A buffer with a large capacity contains large concentrations of buffering components and so can absorb a relatively large amount of protons or hydroxide ions and show little pH change. The pH of a buffered solution is determined by the ratio of the conjugate base to acid. And the buffer capacity is determined by the magnitudes of those concentrations. So we want to calculate the pH of a buffer solution, which is made with 0.15 molar formic acid and 0.20 molar sodium formate. So this is a weak acid and a salt of its conjugate base in a solution, so it's a buffer solution. And we want to calculate what the pH is. So first we're going to think about what the major species are in the solution. We're going to choose the species that dominates the reaction. We're going to make our ice chart, calculate X from our K expression, use our 5% rule, and then calculate the pH of the solution. So in this particular example, our major species in our buffer solution are formic acid, sodium formate, and water. Remember that sodium formate will dissociate into sodium ions and formate ions. The sodium ions won't be involved in the reaction, but the formic acid and the formate ions will. Now the Ka value for formic acid is 1.8 times 10 to the minus 4, which means that the Kb for formate is around 10 to the minus 10. And water is 10 to the minus 14. So since the formic acid has the larger K value, that's going to start our reaction off. So that formic acid is going to dissociate into hydrogen ions and formate ions. So we've got our reaction. We're going to fill our values into our ice chart, write our K expression, plug in the numbers, and solve for X. So in this case, X is going to equal 1.4 times 10 to the minus 4, which is the concentration of hydrogen ions. The 5% rule shows us that X is insignificant in the problem, and the negative log of 1.4 times 10 to the minus 4 will give us the pH. So the pH of this buffer solution is 3.87. Now we want to calculate the pH of the solution after we add 10 milliliters of 12 molar sodium hydroxide. And we're going to think about the same steps that we've used before. We want to list the major species that are in the solution, choose what's going to be reacting, make our ice chart, but this time because we're dealing with a strong base, we're going to be looking at a limiting reactant problem in our ice chart, and then from there calculate the pH of our solution. So the major species in this solution are the formate ion, the sodium formate ion, and the hydroxide ion that we're adding to that buffer solution. Whenever we have a strong acid or a strong base in a problem, it is always where we start the reaction. So the hydroxide ions are going to react with something in that buffer solution to neutralize that base. Bases react with acids, so the hydroxide ion is going to react with the formic acid in the buffer solution. And we're going to produce formate ions and water. Notice that the arrow is going in one direction because strong bases and strong acids react to completion. Because we're mixing two solutions together, we need to calculate the moles of all the components in the solution. So we'll take the molarity of the formic acid, multiply it by its volume, and that will give us the moles of the formic acid. We'll take the molarity of the formate ion, multiply it by the volume, and that'll give us the moles of the formate ion. And take the molarity of the hydroxide ion and multiply it by the volume, and that'll give us the moles of the hydroxide ion. We'll take these values and plug them into our ice chart. So our initial moles of hydroxide is 0.12. Our initial moles of formic acid are 0.075, and our initial moles of formate ion are 0.100. Now we know that strong acids and strong bases react to completion, but when we look at this particular problem, the hydroxide ions are not the limiting reactant. We don't have enough formic acid to react with all of the hydroxide that was added to that buffer solution. So we have exceeded the buffer capacity. That means that we're going to have excess hydroxide ions in the solution, and we can calculate the pH directly from that. So if we started out with 0.12 moles of hydroxide ion and 0.075 moles can react before we run out of formic acid, after the reaction is complete, we're going to have 0.045 moles of hydroxide ion. If we take that value and multiply it by the new volume of the solution, which is 500 milliliters plus 10 milliliters, or 510 milliliters, that'll give us the concentration of the hydroxide ion as 0.0822. If we take the negative log of that, that will give us the pOH, which is 1.05. And if we subtract that from 14, that'll give us the pH. So the pH of this solution is 12.95. So let's look back at the beginning of this problem. When we first had just our buffer solution, which contained the formic acid and the formate ion, our pH was 3.87. We added a strong base to that, but we exceeded the capacity of this particular buffer, and our pH went all the way up to 12.95. So although buffer solutions can resist a change in pH, there are limits to the buffer's capacity. And that's dependent on what the concentration of the components of the original buffer solution are.